All right, ladies and gentlemen, today we're going to talk about distances in the universe. And the essential question for these notes are, how do we measure distances in space? So we're going to start by talking about our neighborhood, which is our solar system. You can think of, your house as planet Earth, and your neighborhood, or the other people that live nearby in your street, as the solar system. So in our solar system, we have a star, which is surrounded by planets, moons, asteroids, comets, dust, gas, and any other objects that might be orbiting that star. And this is true of any star. Remember that our sun is just one star, and every star that you see in the sky is its own sun, possibly with its own planets there. And these are all held together by gravity. Right? So let's take a look at this picture. This is a pretty terrible picture. And the main reason is that it's completely inaccurate, right? So when you look at this picture, it looks like, all the planets are clumped all the way close together, and, they're all almost the same size as each other and almost the same size. Like, the sun is pretty big, but, it's not that much bigger than the planets there. Whereas in reality, if the sun was actually this size, the Earth would actually be probably like a little speck, like, right next to the sun over there. And these distances would be nowhere near as close together as they are shown in this picture. They're probably just doing this so that they can fit everything, into one picture. But in fact, it would take, ridiculous amounts of time to get from one planet to the next, right? So to get to Mars, it looks like it would just take, I just got to jump right over. But it actually takes probably about a 9-month journey just to get to Mars. It's almost a year. So these distances are hard to describe. These distances are hard to describe using just kilometers. Now, kilometers works well on Earth, right? But that'd be like trying to use, centimeters or inches to measure the distance from your house all the way to, the end of the street or your neighborhood. So we have a different unit that we're going to use instead, an astronomical unit. So astronomers often use the distance of the Earth from the sun as this measurement of distance, and we call it an astronomical unit. That's AU for short. And that unit, or that distance, is actually equal to about 150 million kilometers. 150 million kilometers. That'd be like traveling all the way around the Earth, circumnavigating the Earth, which, most people don't even do in their entire lifetime. That'd be like going all the way around the Earth about 15,000 times, right? So going across around the Earth 15,000 times. So that's a pretty big distance there, right? In miles, that'd be 93 million miles, right? So this is a good unit for measuring things within our solar system. This is a good drawing for you to put into your notes here. You have the sun, you've got the Earth. Now, again, this is not a great picture because the Earth is much smaller than it's shown in this picture, right? And the Earth does not travel on a completely circular path. I mean, it's mostly circular. So when we say the distance from the Earth to the sun, we're usually talking about the average distance from the Earth to the sun, because at some points in the year, it might be closer. At some points, it might be further. But keep in mind, remember that summer is not when the Earth is closer. Right? That's not always the case. All right. So here's some distances within our solar system. For instance, between the different planets. Right. So Mercury and Venus, they are actually closer to the sun than the Earth is. So they have less than 1 AU of distance away from the sun, whereas Earth has exactly 1 AU of distance away from the sun, because that's how you define an astronomical unit, right? It's one Earth distance, or one distance away from the sun from Earth. Mars, Jupiter, Saturn, and the rest of the planets, they are all further away from the sun than the Earth is, so they have larger than 1 AU of distance. So Pluto, as you can see there, even though it's not a planet anymore, we consider it about a dwarf planet, is about 40 astronomical units away from the sun. So it's pretty darn far away. So what about if we're measuring things outside of our neighborhood, right? Let's say that you wanted to figure out, how far is your house, not, within your neighborhood, but how far is it from, another house 2 states away, right? Or another country away, maybe. You would not use things like, feet, to measure that distance. You would use something different, right? Something larger. Now, that's the case as well for measuring things outside of our solar system. Remember that the next nearest star, it would take us 100,000 years. And that's 20 times the entire length of Earth's history, or the human history on the Earth, since, the beginning of the pyramids and all that. That's 20 times that amount of time to get to just our next neighbor star. That'd be like if your next door neighbor didn't live right next to you, but lived, in another country, and that was like the next closest person to you, right? And everybody else, there's nobody else in between. So the stars are pretty far away. So we have to use a different unit other than astronomical units. So we already know that astronomical units are already really big. Light years are way, way bigger. So what is a light year? A light year is defined as the distance that light travels through space in 1 year. Now, light is the fastest thing that there is in the universe. Nothing travels faster than light in the universe, right? So light actually can travel 300,000 kilometers per second. Right? That's like going around the Earth 8 times in 1 second, just 1 second, right? So if you were a beam of light, you could go all the way around the Earth, 8 whole times before your second was up. Now, if we wait for an entire year, like let's say you turned on a flashlight and then you waited for a year and then try to figure out how far that light had gone, that's going to be a pretty big distance. So in this case, that distance, you can't even write it as a regular number because there'd just be too many zeros. It'd be 9.46 times 10 to the 12 kilometers. Now, this is scientific notation, something that you're going to be working on today as well. So what this means is that you have a decimal point here. That means you're going to move that decimal point 12 times to the left over there. Right? So 12 times, to the right over there. So that'd be 946 and then 10 more zeros past this number there. So it's a huge number of kilometers, right? So keep in mind again, we said that the nearest stars to us were 5 light years away. It means even if you could travel as fast as the fastest thing in the universe, light, it would still take you 5 whole years to get there, right? But again, we can't, right? Even when we're traveling thousands of miles an hour, which is extremely fast, it would still take us 100,000 years to get there. So it's pretty darn far. So in miles, that's going to be about 5 trillion or 6 trillion miles. So light years are a common way to measure distance outside of our solar system, right? We're not talking about distance between planets, but say the distance between, our star and the next star, right? Just our next nearest neighbor. Not to mention, the 399.999 billion other billion other stars that exist in our galaxy, just within our galaxy. We would be using light years to measure that distance. So here's an object, out in space. It's a pretty large object. It's the Crab Nebula. It's the remnant of an exploded star, so a star that went supernova. And we know that it is 6 light years wide. That means if somebody right here shined a flashlight, somebody over here wouldn't get it until 6 years later, right? So in fact, when we're looking at the light from Proxima Centauri, which is the star that's nearest to us, again, it's 5 light years away. We're seeing that star as it looked 5 years in the past, right? So it's 5 years old light. The same thing happens actually with our sun. So our sun, again, is pretty far away. It's 1 AU away from us. So it takes light a little bit of time to get from the sun to the Earth. It's not necessarily instantaneous. It takes actually about 8 minutes for light from the sun to actually reach the Earth. So when you're looking at the sun, you're actually looking at the sun, 8 minutes in the past, right? So the sun could be exploding, right now, and you wouldn't have any idea until, 8 minutes from now, right? Because you're not seeing that light until it gets to you, which, takes 8 minutes to get to you. All right, so we're going to do some practice. I want you to figure out whether or not you would use astronomical units or light years to measure the following distances. And you can just write this as a little note, on your notes somewhere. So again, astronomical units, just as a recap, that's used within our solar system, right? And light years, again, that's used outside of our solar system. And the first one is the distance between the Milky Way and a lenticular galaxy. Lenticular galaxy just meaning another galaxy that's nearby. So the correct unit of distance that you'd measure there would be in light years, not in astronomical units, right? We're talking about astronomical units just for our solar system. But remember, the Milky Way contains hundreds of billions of solar systems in there, right? And between each star there's just a vast amount of space between each one. They're not close together at all. I mean, they're close together relatively speaking, but in general, not to us. So between our galaxy and another galaxy, that amount of distance is just almost mind-boggling. You can barely imagine it. It's just so really, really far away between each other. The distance between the sun and Betelgeuse, which is a red a supergiant star that might possibly go supernova within the next million years or so. And if it does, scientists say it'll be about as bright as the sun in the sky. So, what would you use to measure that? You can pause the video and make your guess. All right, so the distance here that you would use, or the unit of distance that you'd use, would actually be light years again, because we're looking at things that are outside of our solar system, between one star and another star, right? So that's a huge amount of distance between these two things. The distance between Mars and Jupiter. Distance between Mars and Jupiter. All right, now this distance is much closer together than, two stars are to each other. So Mars and Jupiter, even though they're pretty far away, considering, our frame of reference, how we look at distances, within our own planet, again, that's still going to be a large number to us. But compared to, the distance between two stars, it'd be much closer. So it's within our solar system. So we'd actually use astronomical units to measure this. Astronomical units. All right, the distance between two stars. All right, again, this is the distance between two stars. This is definitely outside of our neighborhood, outside of our solar system, right? So that'd be like looking at the difference between two states or something, if you're thinking about the solar system as our neighborhood. So you'd actually use, again, light years to measure this, not astronomical units. You can use light years because they're very, very far apart. The distance between Venus and Earth. All right, Venus and Earth are both planets within our solar system. In fact, they're actually right next to each other. So the best unit of measurement to measure these would be astronomical units, because we're measuring distances within our own solar system. All right, so you can feel free to rewind to any part of the video that you missed notes from. You can pause at any time. Your homework for tonight will be to finish off summaries and diagrams for these notes. Also, the next step, make sure you're following the next step on that checklist and you're getting those assignments done before the end of the period today. All right, good luck.